stewards of the land and the enduring relationship that exists between them and their traditional territories. The land on which we sit is the traditional unceded territory of the Wampanoag Nation. We acknowledge the painful history of genocide and forced occupation of their territory, and we honor and respect the many diverse indigenous people connected to this land on which we gather from time immemorial. I'll now turn it over to my colleague, Christoph Reinhardt, who is the director of the Building Technology Group, and he'll introduce our speaker. Christoph.
Thanks a lot, Les. Welcome everybody online and in person. Thank you all for coming. I'm really excited about tonight's lecture. As you can see online, you can just Google Timur Dogan. He's a professor at Cornell and he's a member of Solemma, a software company. I just wanted to not talk about the many accolades that Timur has gathered over the years because you can Google them. I just want to more talk about what I know about Timur and how he got into what he's doing today. He actually studied architecture in Darmstadt, which is the place where the Passivhaus Institute Germany was founded. And so the education was really much based on developing solid buildings that are sustainable and combine design with practicality. And then I think what happened during a guest lecture, he talked to Matthias Schuler from Transolar and said, well, I really am dissatisfied with how I learn about passive design strategies. I want to really implement them in my design. And then Matthias said, well, you should come to Harvard. And that's where Timur and I met. And I tried to teach, we were starting at the time to teach these tools. And obviously Timur felt the tools were inadequate because he started programming his own tools. And I think what is really interesting is that he didn't know, I think when I met him, to program a single line of code, which I think tells us all that it's really about having good ideas and coming from a spot where you understand what people might want to do with tools, and then you learn how to do the programming itself. And I think that has always distinguished Timur, and obviously retooling sustainable design is part of the title today. You will see a plethora of different tools that he's developed over the years. And it's always, I think, he's starting from this notion of who will use that tool and how is that tool something that that a few people will really want to apply and use in practice. I would call his approach to his work, he's fearless, obsessive, and paranoid about his text. And I think at MIT that's a compliment. And I think you see that in all the different tools that he's developing. And I haven't seen an overview of his work in years, so I'm really excited. Please help me welcome Timur, and thanks a lot for joining us.
Well, thank you so much for the introduction, Christoph. It's such a great pleasure to be here today. Thanks for the invitation. It's wonderful to be kind of back at MIT, where kind of some of the ideas of what I will be talking about, I think, originated. Just briefly, at Cornell, I'm directing an M.Arch program, and I'm teaching the core curriculum classes in environmental systems. That's kind of basic building physics, and then going more into kind of building performance analysis and so forth. Occasionally, I get to teach a research seminar and also design studios, and that's really important for me to kind of mention because I think ultimately when you develop software tools, like bringing that together with design, that's I think the kind of the ultimate challenge for me. I also direct a small research lab, cross-disciplinary group called Environmental Systems Lab, and currently consists of 3 systems engineering students, 1 planning Ph.D. student, a postdoc, and 6 undergraduate researchers. And I want to kind of mention them today and thank them here for all their dedication and hard work. And you'll see some of the work which without them wouldn't really be possible at all. So just to kind of start off, like what motivates us? And I think it's these 2 overarching questions, like how do we build sustainable and livable cities for 2 billion new urban dwellers? That's, if you think about it, 250 times New York City, the population of New York City. And then how do we decarbonize the built environment and mitigate climate change? If you look at the diagram on the left, you see that more than 50% really is attributable to the built environment, how we construct cities, how we build our buildings. And the underlying philosophy to me is like, I always, coming from an architectural background, I always understood design to be a smart response to the environment, to the context, to the site, and to really enable designers to create these kind of responses to the environment. I think we can help that with augmenting and informing the design process with building technology, with software tools and data to help them, help us as designers arrive at better performing solutions more quickly. And it's a multi-objective challenge where we need to look at many different variables like energy and carbon, active mobility, comfort and well-being, daylighting. So they're all kind of proxies for quality of life, if you will, as architects that we're kind of striving towards creating a more livable kind of environment for us humans. And well, in the design process, however, one of the biggest challenges today, I think, is that analysis really happens too late in the design process, in the creative process. And this is actually borrowing from a systems engineering theory where that came out of shipbuilding. So you see kind of the reference at the bottom, where they really researched this kind of understanding where you can, what happens when you bring information, data into the decision-making process early on. You can basically influence the design more radically, more quickly, with a reduced cost. And so what are the ingredients really that we need to kind of move this evaluation of design, use of data in design earlier into the design process? And to me, it's kind of these four components that you see on the left-hand side, which is integrated tools that really are easy to use and lower the barrier of entry to people who are designing, who are the creative thinkers, but not necessarily trained as engineers. We need new metrics that support their design narratives and not necessarily kind of the established way of measuring performance in a building. And we need new algorithms to reduce the computational complexity, to be more responsive, to give feedback in a timely manner. And then the fourth one, the last one, really is about use of data and use of big data. We're collecting more and more data of our built environment, of our daily lives in cities. How can we leverage that as designers to create more informed design decisions? And so this is, I want to share like a cross-section of my work that touches upon these kind of four main points today. So integrated tools, this is a screenshot of a software called ClimateStudio, an advanced daylighting energy simulation tool that seamlessly integrates into Rhino, which is a popular design environment and provides direct visual performance feedback during the design process. So this software has its roots to what Christoph mentioned, kind of the early times when I was still a student working with Christoph and 3 other collaborators back at Harvard and MIT. And it's one of those kind of, I think, tools that offer these highly integrative workflows directly embedded in an architectural design environment. And it's used widely in practice and taught in over 400 universities worldwide. Just to kind of show you how you could use a software like that in the design process, I'm going to kind of walk through a really, really quick case study. And I'm not going to do the architecture any justice, but just to kind of explain the principle. So imagine you had a highly insulated house with very low thermal mass. In this case, it's a school built out of hay blocks in Denmark, where you quickly see that with the amount of openings that you're controlling here, you get an overheating problem. And how can you mitigate that? And what is how can you find the right balance between the openings that are there for views and daylight, the energy consumption that is kind of a function of that, as well as the kind of indoor thermal comfort here mapped spatially, where you see red is basically overheating just because of the increasing in solar gains and the mean radiant temperature in the space. So with that being easy, now that any design student in the world can do this kind of analysis, that quickly it really becomes more about the intellectual challenge and connecting kind of these analyses analysis methodologies with the design narratives. And that's kind of in my teaching what I find more and more to be the case, and that's actually the exciting part, where we kind of get to kind of combine design thinking with this kind of analysis. And but we also have to be critical of the metrics that we are using. So as architects, we need to participate in the development of new metrics and make sure that these do actually capture the things that we care about. And let me give you, I'm going to give you 2 examples of kind of some of the recent work that we've been doing. So this is showing you the state of the art of daylight analysis in buildings. So we're looking at as a 3-dimensional model. We can simulate the illuminance profiles in that space. And then typically what we do, we pair this with an occupancy schedule and a target illuminance that is is a minimum requirement in the space so that you can kind of perform your seeing task. And then that can be summarized statistically in a metric that we call daylight autonomy that you kind of see plotted on the left-hand side. And it's a great metric, don't get me wrong, but it's primarily developed for work environments. And the question is, like, can we translate that into other building uses, for example? And when I think back in my kind of times as a student, when I was thinking about daylight in architecture, I was thinking very differently about it, and especially in residential architecture, where, for example, the presence of direct sunlight is not always a bad thing, whereas in the office environment, we think about it as a glare problem, and the way we diffusely light a space in an residential architectural setting. And so this is work by an undergraduate student who I actually met in the first semester at Cornell, which was very exciting to work with him over 5 years of his kind of B.Arch degree, where he kind of basically dissected the way we are really simulating daylight in buildings. He looked at kind of, can we visualize the amount of light in kind of these seasonal and diurnal bins, and then talk about it more qualitatively. And you can see there's a drastic difference, obviously, and the average that we tend to always look at as kind of daylight simulation modelers is kind of not really kind of conveying the temporal differences. So in the winter evenings and winter mornings, there's barely any light in the space, and then in the summer you have a fully lit, fully daylit space. And so this is coming out of a series of papers that were kind of talking about the subject matter, and I think the final result was the scorecard, where you could quickly see which apartment really is for you, right? So with just a glance, you can understand, when does this apartment have access to direct sunlight? When does this apartment, when is it sufficiently lit by daylight, and when is there not enough light in the space? So you can kind of understand the temporal fluctuations really quickly, and think about what that means for you as a potential occupant. If you're a more morning person, you really do want the direct sunlight on the balcony or on your kind of kitchen window or so forth. And if you're more an evening person, then maybe the evening sun is more important. And I think that's something that this metric highlights really beautifully. The second example that I want to bring about is talking about view. So we consider that a design quality, kind of talking about views to the outside, view relationships between spaces on the inside. And as you can see in this example, I think you all know the architects, but the architects were clearly thinking about that, right? So there's diagrams that are evidence of this, and there's, I think, a beautiful kind of way of dealing with spaces that orient themselves towards the outside, look outside, have a clear view relationship with the outside, and then spaces that are much more introverted, that actually more look inwards into a courtyard, or have very, very kind of small, or relatively smaller openings to the outside to kind of frame the views. And these ideas are really difficult to grasp in building science terms, let's say. We all know that there are benefits to view. In hospital wards, patients recover more quickly with view. There's measurable work performance in spaces with good view. And Christoph Irmak's work and Andreas Czegut's work showed that there's a increase in real estate value if you have good views. But the metrics that we agreed upon as a practice or as a profession, like, for example, Leeds view analysis and the European standard for measuring kind of view, really shortchange architects in that kind of way of thinking, where it's more of a pass-fail, just preventing the worst-case scenario, basically a windowless building. And so we started this multi-university research initiative where we kind of thinking about, together with Stefano and Won-hee, Stefano Schiavone at Berkeley and Won-hee at New Jersey Institute of Technology, to kind of think about ways how we could collect data together in a meaningful way, kind of coordinate experiments, and kind of plan how we want to collect data together so we can collect a sufficiently large amount of data to capture all of these different nuances about views. So we're kind of planning for online surveys, VR experiments, and we're asking really fundamental questions like, how can you use VR experiments for these kinds of analyses, and how are the results then biased and so forth. But this is all, I think, more kind of a long shot, but there are some preliminary results that I want to share. And this is kind of work by a PhD student in my lab, Jae-ha Kim, who has basically developed this survey as a preliminary work and input around about 1,000 different view scenarios. And we now have over 300 participants that ranked these 1,000 view scenarios. So we have a very, very diverse set of view scenarios that then hopefully capture what one would be able to encounter in a design process. And then we trained a machine learning model that then can do this view satisfaction ranking of the space. And you see kind of much more fine nuances in the results. And again, this is preliminary data. And we all hope that you participate, either as part of the research group planning the view experiments together, or if you just want to kind of help train our models, then you can help us with just doing the survey. All right, I'm jumping in scale from building scale to urban scale. So when we talk about buildings, of course, and when we design them, looking at what happens around our buildings is also an important thing, and as designers, we do care about that. And our doing actually has a huge influence on that as well. As you see in this, I always use this kind of photograph by Foster and Partners that they did for pitching their design ideas for the master city design in Abu Dhabi. So this is both in Abu Dhabi, one shot taken basically at the city center with streetscapes that are basically unbearable to walk in or spend any time, and then using kind of more vernacular strategies to kind of with buildings and self-shading, you can drastically lower the kind of outdoor thermal comfort issues that you would encounter in the same kind of climatic environment. And here we have really good metrics, like one of the popular metrics to measure outdoor thermal comfort or the human response to the microclimate is this metric called Universal Thermal Climate Index. It's basically a very, very simple model where you input a bunch of meteorological parameters, and they have a simple fitted function that spares to do or saves you from doing all of the modeling, like the clothing model and the heat transfer model on the and so forth, and can predict heat stress that you're facing. But the challenge here you can kind of measure these with weather stations, right? But when you're doing a design, you have to have some kind of way to predict these meteorological inputs, right? So you need to predict air temperature, radiation, humidity, and wind. And there's been a lot of great work coming out of MIT. I'm thinking of the Urban Weather Generator by Lest that we are using quite a lot to kind of predict the temperature, radiation levels, and maybe the humidity levels. But for the wind variable turned out to be a huge issue for us. And so we've developed a software tool called Eddy. Some of you have maybe used and have struggled using it. And this is just, I think, the nature of CFD. But we tried our best to kind of implement and automate best practice guidelines in CFD to kind of make it as easy as possible to use and to run these kind of CFD analyses in early design. There's also an MRT component within it and so forth. And so it's kind of a multi-physics simulation that we also validated for long periods of time through measurements over on the campus, and I don't want to bore you with the details, but it worked pretty well. And why should you care as a designer? So this is kind of this kind of graph came out of a collaboration with Sidework Labs, actually, and then a student took it in a design studio and kind of developed it further, kind of thinking about what strategies in Toronto, when you develop the waterfront, what strategies could you use or what could you achieve if you were able to kind of design with the microclimate in mind. And so the strategies are very simple: protect from the sun in the summer and expose people to the sun in the winter, shelter from wind in the winter, and expose people to the wind in the summer. And if you achieve that through kind of these diagramming, what does that mean for the thermal perception in the spaces or in the outdoor spaces? You achieve 26% increase in comfort hours. What does that really mean? If you look at the diagram at the bottom, it's basically 4 additional months where it's comfortable outdoors. And I think that's a huge value proposition. If you think about a restaurant owner who can use the outdoor seating for 4 months longer in the year, if you think about a person walking or biking, or even kind of motivating that person to walk or bike, if your city is basically comfortable for 4 more months in the year. And I already alluded at it. Using Eddy is still painful. It's very, very slow. And the huge bottleneck is the CFD. So we have been thinking long and hard on how to kind of make this faster. And so we've started training a surrogate model using a general adversarial network, a very popular one in style transfer called Pix2Pix, where ultimately the challenge really was in this project to provide all the training data. So we used a highly automated training pipeline. We bought lots of fancy big computers, and we let it simulate for over a year. And this is kind of a trained model after a year or so of simulations, where you're basically pairing kind of a ground truth image with a rasterized top view of the city, and the model then learns to kind of do the style transfer, basically. It learns how to paint in between the building masses these CFD responses. And what you see over there is not kind of sped up. It's kind of takes really just a few milliseconds to compute the wind patterns at the pedestrian head height. And that, for the first time, allows you to kind of interactively play with these CFD simulations, kind of pushing and pulling, massing around. And it's quite surprising what it can do, and it's also important to mention what it can't do. So what you see here is a comparison of kind of these predictions using the GAN versus simulation results simulated with OpenFOAM. And it's quite remarkable how well it gets the overall picture, and this is done with an already outdated model that was trained in the winter, and by now we have a lot more training data, and so we should probably try it again and see if we can even get rid of some of the errors. But what it's important to know is that the overall average result is pretty good. There are some spots where there's severe errors, and that's especially in places where there's turbulence or some kind of jets that are forming that the GAN just doesn't know how to replicate. So this is an exciting research kind of project that I think is still ongoing, so stay tuned. Now, that brings me to my last talking point. As I said, we are collecting more and more data about our built environment, how we live in it. And I would like to talk a bit about tools that help us leverage this data in design and to help us understand systems and relationships that are kind of embedded in this data, but not always maybe immediately visible. And I want to start with mobility in a sense, right? We said we are interested in designing sustainable cities, and almost 30% of that was mobility related, right? When we talk about carbon emissions in cities. So can we design or redesign our congested cities and make them more walkable? And there's, of course, a lot of kind of benefits that can be attributed to this, health benefits, financial benefits, property value benefits, and of course the reduction in greenhouse gases that we can look at. So we started, again, trying to leverage publicly available data. So we collected data from the census, we collected data from the Federal Highway Administration that run travel surveys, and in some states they do this with add-on data that provides us with a pairing of demographic data with origin-destination matrices, so kind of where do people go, for what reason, and what mode do they choose. And that data we leverage and combine with all other important urban data that you can use to describe the built environment, like job counts, population densities, and so forth. And then with this data set, we trained basically a series of models that do the activity choice, mode choice, destination choice, and trip length prediction all in one go. And then that allows us to basically simulate mobility patterns in cities. And we can simulate things like visitor catchment, like where do people spend time when, and so basically creating this OD matrix of trips. And then we use a fairly standard kind of mechanism to route people through the city depending on the mode. And that's kind of our raw data, right? And from that data, we can then infer energy use, or how much gas people will use, or how much electricity if we talk about electric cars. We can infer how much time they spend commuting. We can talk about pollution. We can talk about health benefits, and we can talk about resilience, right? And of course, validation is important, and we are in the middle of validation. This is just one chunk of it where we try to validate these predictions that are done by our software called Urbano against cell phone data. And in this case, this cell phone data was provided by SafeGraph. And it's maybe important to note that cell phone data can also be heavily biased. Actually, this data set works well in really dense cities, but does not work so well in suburbs, or because the data is so sparse that you can't really kind of infer anything from it. But so here we validated our predictions in Los Angeles, kind of trying to comparing visually. So this is also another really important thing to mention. You can really only validate the patterns, but not the absolute numbers against the cell phone data, because you always get some form of sample and you don't know exactly the total number of people. But we do have fairly good data on that from the census. So comparing that, it's kind of remarkable that just with this kind of publicly available data, you can then predict mobility patterns that are basically indistinguishable from cell phone data. And if you think about that aggregated cell phone data, getting access to that is very difficult, or not difficult, but it's expensive, and therefore really not easily accessible for designers. And then the other thing is we can simulate scenarios that don't exist. We can now modify the city and then predict what the changes are and so forth. So you can think about, if you think about this as a case study where we added some new program, new housing, new jobs to a neighborhood, and then can see how that changes the mode choices, for example, here kind of showing you where people start walking more and where people actually start walking less because they want to drive to that new desirable location. And then you can do things like adding a transit line, for example, and see what that does to your kind of mode distributions and trip lengths and so forth. And the other great thing about these models is that we can basically pair the model and retrain the model with qualitative parameters. So you could imagine you could pair it with some kind of street quality index or anything you can imagine as an urban designer. You can kind of pair the model with if you have enough information about how that, the state of that variable, if you will, is distributed over the city. We did it with outdoor thermal comfort because of course we were interested in combining kind of our models that we developed for Eddy and then the Urbano simulations, and to see whether the outdoor thermal comfort really is a driver or a way to motivate people to walk more in neighborhoods. And we kind of created these simplified canyon models, simulated outdoor thermal comfort for the entire city, and then basically asked our machine learning model how the mode shift will change if you had perfect thermal comfort in the city year-round. And you see a very, very strong shift in the cold weather, like with decreasing comfort, people start shifting. In high density neighborhoods, they shift into public transit and back, and that's almost 4%. The vehicle use is fairly constant in that data, and then we did a separate kind of analysis for the less denser parts of the neighborhood, and we are hoping that we want to repeat this, I think, in more and more cities to really understand those patterns a little bit better. But if you think about this 4% change in mode, that's quite significant. So I think California has the goal to shift mode towards active mobility by 6 to 8% for 2030. And if you can do 4% with outdoor thermal comfort alone, that's quite a significant number. And so we packaged all of this in a software tool called Urbano, and it's the first time I'm going to say, don't download this version. There's going to be a new version that can do what I just talked about in a month or so. I mean, by all means, download it if you want, but just letting you know that there's a new version in the works. Now, the city of Ithaca, where Cornell is based, it's a very small city, but it's very progressive. So they kind of decided that they want to be carbon neutral by 2030. And so we kind of volunteered and jumped in and said we would like to help you with that. We would like to leverage some of the modeling techniques that we've developed to maybe guide some of the policy making, inform the decision making with that. And if you look at it, this is an estimate from the city. 40% is carbon emissions are estimated to be from building operation. The other 40 are estimated to be from transportation. And so the strategies that we suggested that we wanted to look at is, of course, we want to electrify the mobilities, the vehicles. We want to shift more towards active mobility modes. We want to leverage and change the way we think about energy supply, and we want to look in depth at the buildings, thinking about where do buildings need to be upgraded, where can we simply swap the systems. And then this is a project that I'm doing together with my colleagues, Felix Heisel, who's very, very interested in kind of turning Ithaca into a circular economy. And so I talked about big data and data availability, and now basically we find out it's all about big data gaps, right? So we can't easily do this in a city like Ithaca, even though they have a very, 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 very good planning department that curates all the data that they manage, but it's still not enough. So we started off by creating a catalog of construction typologies to really understand how the buildings are made, what are they made out of, and then a student team kind of went and took a bunch of drones and developed workflows to create from photogrammetry models, create basically segmented models that we can understand, like how much window area does a building have, and how much facade area does it have, how much roof area does it have. And that allowed us then to create a solar map showing kind of the photovoltaic potential on every rooftop, taking into account vegetation and so forth. And this is modeled after a method that Christoph and Alston developed here at MIT back then, and we kind of applied it to the city using kind of these kind of three more high fidelity 3D models that we had created. And we also built energy models for every building in the city, and then now can compare the two, kind of the production potential and the demand. And you can see in these kind of scenarios that are plotted here, so this is kind of the total energy consumption of the city of Ithaca, kind of all buildings aggregated in monthly shape. And then we're planning with this kind of electrification alone. You can basically push the red heating curve, if you will, or gas consumption. You can push that down to somewhere where the dotted red line is. And then plotted against that is the PV production potential. And of course, we're trying to kind of understand how much is the right amount of PV on the rooftops, because you saw in the map before, some roofs are great for it, like big box stores. Some other roofs, we have a lot of small single-family houses, are maybe not ideal for kind of large PV installations. But, and again, this is work in progress, but what you can see on this chart already is that on paper, decarbonizing the city is probably very doable, right? So if we choose a more ambitious scenario, we can get a load match, at least at the annual level, that is around 80%, maybe going even to the 90%, which I think is a little bit unrealistic. But that's not taking into account hydropower that we have. It's not taking into account solar farms that are kind of on agricultural land, for example. So I think Ithaca has a lot of potential to kind of green its grid. So I think the on-site PV doesn't have to do it all. So this is very, very encouraging, right? So you might ask, like, why is it not happening, right? Why is this not happening and quickly? And I think there's a couple of things that we need to address that are maybe beyond the kind of engineering solutions for this. I think the technology is all there, and the potentials are all there, and now it's really kind of time to make decisions, and that we have to involve everyone in this. And I think, so this was a big part in the Ithaca Green New Deal is equity and justice, and just had a wonderful conversation with Christoph about that there's actually incentives out there that work against decarbonization and that can potentially threaten people to be gentrified out of their own home. Because if you invest in your house, if you renovate your house, your property tax will go up. And all of a sudden, people that invest money in decarbonizing their home might actually be priced out of their own house. And so there are kind of policy level challenges that have to be overcome. And then, of course, we have to think about how do we bring people on board. And then once we achieve that, like, how can we actually do this? 2030 is not that far out. And I don't think there's enough contractors to renovate Ithaca, right? In that time scale. So we have to really think about ways to accelerate renovation work, think about ways to do this in a non-disruptive manner. And I'm kind of just copying an idea here from the Dutch, which is called Energiesprong Initiative, where they're kind of trying to serialize the production of retrofitting panels. And of course, that works on simple geometry as well. But Ithaca's houses are very complex and very playful. So how can we do that? And I think that's a huge challenge to deal with. I want to end with a slide from the failed Sidewalk Labs Toronto waterfront development, which I think was super encouraging, right? So we did all the simulation work. Some of the software tools for outdoor comfort and mobility were part of team at KPF. And I think this is another key driver why you should be thinking about quantifying some of the things that you're doing as architects, some of the good things, obviously, because it can help to have discussions with non-designers. And this was kind of a community engagement workshop for that waterfront development. And I think we're planning something exactly like that for Ithaca, because it's a huge issue to bring everyone on board, to explain what's at stake, to explain what the benefits would be if you would do X over Y. And this was a really nice way, and a kind of playful way, to kind of engage with non-designers and make them or teach them about, like, the relationships between a walkable city, a sprawled city, the energy consequences, and so forth. And one of the participants started out kind of wanting this low density environment with lots of green space, but then really understood that this is not walkable. You have to rely on a car and the energy implications. And so I think it's kind of, it's not to convince maybe, but it's to kind of engage in a discussion where I think this kind of data or evidence, these kind of simulations can be incredibly helpful. And so I hope I showed a cross section.
Yeah, thanks so much for this amazing presentation. We're going to start off with some questions. Does anyone have any questions from the audience? Maybe, otherwise, I'll start. I'm also a PhD student in Christoph's lab, and it was amazing to see all the incredible tools that you have developed over the last years. I would be curious to hear a bit more about simplifications and how you deal with that in your tools, right? Your tools target very different audiences, from highly skilled engineers who might use CFD analysis to architecture students who are maybe curious to use these things for design, to maybe regular people who live in Ithaca who want to see how their communities could develop. And so how do you think of designing tools? What do you expose to the user, and how do you deal with this notion of simplification versus when do we actually need expert knowledge, and when would it be maybe misleading to not expose certain things?
Yeah, thank you. That's a really great question. So I think we're always striving for as simple as possible, right? So and sometimes we start developing a tool and we realize by using it ourselves it's too complicated. So that's kind of it's kind of like a trial and error, I would say, and through iterative kind of development, we improve these things. But I think the other component in your question was very interesting and really important, is because you can do so many kind of misleading things, or you can be put on a wrong path doing these simulations if you are if you don't really fully understand what they are doing, right? So there's always kind of an idea of the tool being educational about the engine that is behind it as well. That is, I think, an important thing to incorporate. And sometimes that works, sometimes it doesn't work so well because you have to shield so much complexity. And I want to bring out one example, which is this kind of CFD surrogate model that I presented. And I think we're getting a lot of criticism, and rightfully, from the engineering world, where they say, well, this is, I mean, the machine learning model really doesn't understand any of the physics. How can you be sure that if I feed it X, Y, Z, that it will still produce something that is good? And I think here the tool developer's responsibility is to make sure that the tool can only be used for the things that it has been trained, where that you can guarantee a certain accuracy. The other good thing about the machine learning tool, though, is that it collapses domain knowledge into the training data, right? So as a user, you cannot really do anything wrong anymore, because it's embedded the kind of the best practice CFD, the fact that the CFD simulation converged properly, all of those things are embedded in the training data. And that's one of the beautiful things where you can, I think, forget about the technical constraints and focus on the intellectual kind of exchange you have with the software. And I think that's something that I'm excited to kind of see when we kind of release this in the studios and release this to the public.
Thank you so much. On that note, I'm curious to know your thoughts on using rules of thumb in design and kind of condensing that further, especially with increased amounts of data and ability to look at a wide range. What are your thoughts on using that as a designer?
Yeah, it's also a great question. So, I mean, Christoph mentioned it, right? I complained in my own education, I really complained about rules of thumb. That's because that was all that we were taught, right? But I think it's important to note that they're fantastic, right? Because they help you to kind of establish an intuition and an expectation but on their own, I think they're kind of weak, right? So if you can combine the rules of thumb, kind of understanding how things should be behaving, and then combining that with the ability to actually do some more advanced analysis, then you can kind of really, I think, unlock the potentials that we talked about in sustainable design, and talking about kind of augmenting the design process and helping it kind of achieve better outcomes more quickly. So I do think they're important. You should learn about them. You should understand where they're coming from, and use them as a kind of way to do a sanity check on the analysis that you do.
So for the architecture students out here who like saw, especially maybe the one slide with Toronto where you had like the 26% more outdoor thermal comfort, and you mentioned that you kind of translated some of it into like a design context. So what kind of rule of thumb would you give to the architecture students who wanted to like make more comfortable outdoor environments?
Yeah,
or is that exactly where we should
it was
use
exactly what's on the slide. I mean, depending on the climate, right? But Toronto is cold and windy in the winter, and it can get warm in the summer. So it's really, I think the principles are a no-brainer. If you think about spending time outdoors, you should have an intuition for these things, right? I think the suggestions are also a no-brainer, and you would at some points you might ask yourself, like, why do we need to do the simulation, right? And in some cases you don't need to run a simulation, but it's sometimes really helpful to be able to quantify this, to be able to convince someone else that this is a good idea, right? So if you can make statements like that, where you can say, well, your patio, your balcony will be like, you can use it for 2 months longer, 4 months longer. I think that's a very convincing argument to make. So it's, sometimes you use it to improve your design, sometimes you use it to create a better narrative to pitch your design. Yeah.
I have a bit of an open-ended question. You speak a lot about creating tools that fit really well within existing workflows and that are intuitive and easy to use. And I'm just curious to know what augmenting design means to you in terms of the role of the architect as it kind of evolves into a more digital.
I think the role of the architect fundamentally stays the same, at least in my way of thinking about it. I think the tools are useless if you don't have good ideas, right? So the best uses of these tools that I showed are basically a great idea that you have and you want to interrogate it, you want to test it, you want to refine it, right? Or you want to pitch two really interesting ideas against each other and decide which one is actually performing better or performing the way you intended. I think that's when these things are powerful. But without the design idea and the design intention, they are not creating the architecture for you, right? So they're merely tools to help you understand your designs, and they're ways to, I see them as ways to help you communicate the good that you're doing with your design, yeah?
Okay, thank you so much, Timur. Beautiful work and really presented in really exciting ways. I'm curious about how you feel about simulation for in design contexts where simulation is hard. One of the things that comes up a lot in our teaching and in the work that we do with M.Arch, but in students in general, sometimes there are ideas for buildings that intuitively and with physical evidence work really, really well, especially ideas from vernacular architecture or from history or other parts of the world outside of the West that we know are good, but our simulation tools either can't capture why they're good or that they're good or model them at all. And sometimes we worry, are we sort of leading people away from these good ideas because of the limitations of what we can simulate, or is simulation expanding to meet those? How do you think about that in your work?
Yeah, that's my daily frustration. I mean, I started off with ideas like that myself, and that's what got me into the tool development. I think you're absolutely right. Some of the tools that we leverage on a daily basis are just not designed that way, right? To kind of incorporate the more passive strategies and so forth. There are models, they all have limitations. And I think there's sometimes not enough funding going in that direction, right? Because it's maybe not interesting or not impactful enough at the big scale, if you will, right? And that's, I think, a challenge. And that's why I think architects need to be involved in the development process of the metrics, but also of the tools themselves, because ultimately, an engineer will not design a software that you will love, right? So I think you have to be really careful about that, and I do agree that this problem exists. I think an example to make is natural ventilation. It's very simple. We can actually simulate it really well, but it's still more difficult to simulate than an HVAC system. So if you turn on the AC, your results will be good. The comfort results will be okay, right? But getting a naturally ventilated building to come out right requires lots of refinement, playing with the controls, et cetera, et cetera. So it's true, and it's a challenge. So I think that's maybe when teachers need to kind of step in and motivate students to go in these kind of other directions. And
should I go? Okay. I mean, this is phenomenal. Thank you so much for sharing this. And like, I mean, Timur and I, full disclosure, worked together on my master's thesis, so I'm a little biased here. But so I guess like what's really interesting to me is it seems like technologically we are there, right? Like we have these tools, as you mentioned, really high fidelity simulation tools that even a student can use. We have, you know, the frameworks, and we have the young architects that are using these tools. It seems to me, and that's a little bit of my perspective as well, it seems like the big gap is how do we engage people outside this room with these metrics? And you shared a bunch of examples, right? Like you showed the Sidewalk Labs example where you built this interactive exhibit. You showed the Maptool example that Christoph did years ago, built a web app to put that out in the world that anybody can access, that has an internet connection. That's great. How do you view the evolution of that piece specifically, like the communication of this information to a crowd that's broader than the architecture crowd, and both in terms of how do we do this more effectively, but also are there any new technologies that you're seeing that you think help us do this at scale, right?
Yeah, it's a really tough question. I mean, I think community engagement is something that as researchers we don't, or I particularly don't do often enough, or at all in many projects. And I think that's important, that you kind of speak to people outside of your domain. And that can be scientists and other professions, but it could also be the people that you're actually doing the work for, even if it's indirectly, right? For the people that maybe then end up living in the buildings and so forth. So I think that's an important component. I think we don't do that often enough. But I think with these urban scale projects, decarbonization projects, I think the role of these engagement workshops where you are forced to kind of break down complicated technical relationships in ways that an average person can understand, that I think is a huge challenge, but they have their place there, because ultimately you have to convince these people to make the decision to renovate their house, right? I'm not sure if there are any technologies in particular that would make that easier.
Like how are you all going to put the information about the Ithaca homes out? Like how, let's say I own a home in Ithaca. Like
you could put it on the web, but I think it's also fine if you printed it and then talked with someone on a table. I don't see like a technology in particular being like a dramatic game changer there. Thanks.
Hello. Yeah, thanks. Thank you. My name is Kritika Kharbanda, and I'm a MDes Energy and Environment student from Harvard GSD. Thank you for the presentation, but also playing a major role in digitizing the building industry and helping architects design with being informed by all this data. My question is about the project you showed for decarbonizing Ithaca.
Mm-hmm.
And I think you showed like 40% is through operations, 40% transportation, and I'm assuming the rest 20% is through embodied materials. And you showed that some of the strategies also include weatherization, adding more insulation to buildings to help tackle the operation side of things. My question is, how do you aim to look at the trade-offs between operational and embodied? Because that is, of course, a considerable chunk for decarbonizing.
Yeah, and I think it goes even beyond the simple kind of thinking, simply thinking about embodied carbon content. And it's not my specialty, but my colleague Felix is working on that in depth. And I think they're really thinking about, in that group, they're really thinking about how can we disassemble buildings instead of tearing them down when we have to, right? They're basically taking buildings apart and putting them back together in different forms. So it's a huge economic question. How do you create a market where you can actually then buy, I don't know, like a door or like a beam that was in a 1830 house before. So there's kind of local collaborators like Ithaca Reuse Center and so forth that participate, that have a huge yard where they store these materials, and so they're kind of testing that out and understanding kind of what that has, how that is kind of impacting the economy also, right? So this transformation into a fully circular economy is of course very, very interesting. I think it's, well, the operational energy consumption, I think, is just so pressing to get that fixed, right? It's so pressing, and we shouldn't make the mistake to kind of spray foam everything. We should try to use, obviously, materials that have low embodied carbon content, are somewhat renewable, right? And recyclable. This is where I'm hoping the research will go, that we can kind of really go back to the core architectural profession, detailing this out, kind of how do we do this with these really, really complex buildings, geometrically complex because they've grown organically in some ways, and it's really, really difficult to get them weatherized properly.
Thank you so much, Timur, for your presentation. Very fascinating work. I echo everyone's sentiment. I found that the layout of the presentation with the different sections of the tools, talking about algorithms and methodologies and the data in the end, was really tying everything together and showing also the challenges that we're facing when we're trying to decarbonize. In terms of, there's a lot of inconsistencies in the data set that we have, or there's some missing, there's some gaps in the data, etc. And I'm just curious in terms of your own ways to look at the current data that we have available. For example, you mentioned a catalog of construction typologies. How do you deal with the uncertainties that come with lack of data, basically, in designs?
Yeah, it's a very good question, and I probably don't have an adequate answer. But so these initiatives or projects were ways, really bottom-up approaches or attempts to fill data gaps. And of course, every kind of building is a data point that has a bit of metadata, and we are making a guess, like what kind of construction type would you be finding there. And you can be fairly certain for newer buildings because there were codes, stricter building codes and so forth. You can kind of know what you're going to expect and what you find. For older buildings, it could be anything because it could be the original wall. It could have been retrofitted already and it's not recorded anywhere in permit data and so forth. So there is a huge uncertainty, especially in the thermal envelope properties and how leaky a building is, for example. So our way of dealing with it is trying multiple variations that fit the actually metered energy demand, and then we just have a very huge uncertainty in terms of the results. And I think that the challenge, and I don't think we have a really good solution for that yet, is to kind of then deal with this uncertainty in the decision-making process where you're now thinking about weatherizing, but you're not exactly sure where the demand is or where the wasteful demand is coming from. Is it the windows, the problems? And then you can only solve that when you go to site and actually look at the building, right? So it's maybe a benefit of doing this project in Ithaca. You can actually walk to the buildings, and the size of the city is like not completely overwhelming. Yeah.
Timur, amazingly impressive work and presentation as always. Thank you. I have two questions. One I think is quick, and then the other is more in depth. In the Ithaca decarbonization project, when you say you can load match for the month, are you just thinking in total, or have you also gotten into thinking about the timing? I mean, are you assuming that the grid or batteries can handle the timing of the demand and the supply?
Yeah, excellent question. I mean, Ithaca wants to be carbon neutral, and they're just thinking about the total. We are providing that, but then we're also interested, obviously, in going more in depth. So we haven't really started that part yet, kind of really thinking about the hourly loads and how we could kind of leverage batteries or maybe some other kind of storage systems to kind of deal with this long-term shift. But
makes sense. My second question is your project where you created the synthetic data set with CFD and then ran the GAN, and now you have the really fast modeling time. That seems like the perfect application of this kind of workflow because the CFDs are really slow and they're really difficult and easy to make mistakes. I'm wondering what you think is next. I mean, there's so much potential for this kind of workflow. I mean, what other questions could we be answering with this kind of workflow?
I mean, I think what we implemented there was pretty hackish, and if there was a computer scientist and a CFD expert involved, right, I think you could leverage these machine learning techniques right in the CFD code itself, probably to speed up certain simulations. I think that probably is the better approach because there are some pretty severe limitations of this model, right? So you can't, if you just want to evaluate wind speed just a meter higher, you can't, right? You have to train a new data set that can kind of, or train a new machine learning model that can deliver the slice that is just a little bit higher than the one that we're looking at. So there are some really, really strict limitations of how you can use that. So I think it's an attempt. Maybe it's a cry for help that others jump on board and help us make that better. I don't think kind of, and I had this really great discussion with some of your students, like the machine learning may not be so interesting in kind of domains where we have analytical models that are quick and approximate things and so forth. But to me, what is exciting about it is kind of this ability to be able to quantify the unquantifiable, like more subjective things, like things that relate to kind of a human response to something which is obviously different from person to person. And I think that's where I'm really excited about these models. So we have to think about how we collect data to train these kinds of models, right? And what kind of data do we want to collect?
Thanks.
Yeah, hi Timur. I find this very interesting. I come from the System Design and Management Master's program, so I find curious that from the name and then the graph that you showed from systems engineering approaches from shipbuilding to some other applications, I'm curious about what are the focus in terms maybe of approaches, methodologies that the lab has taken from systems engineering, systems design that might have been helpful in giving an edge to the, let's say, architectural work or traditional work?
Oh yeah, I think I've learned a lot from my systems engineering colleagues. I think we are leveraging so many techniques that they have perfected in a way in their profession. And it has a lot to do with optimization, has a lot to do with dealing with large data sets. And also these kind of machine learning models that I showed to you, I mean, this is something that is not taught in the architecture school. Like students learned that in systems engineering and brought it basically back into the lab. So that's how many of these projects started.
Thanks.
Timur, is a great presentation. You just mentioned analytic models sort of contrasted with machine learning, and I might ask you to speculate about that a little more. And particularly as regards the computation engine that underlies much of what you showed with ClimateStudio and others, Energy Plus. And it's well, do you find that constraining in any way? I have my own views about this, and we can talk about it later, but do you think it enables the kind of say, physics-based explorations that might get you out of a sort of a box of conventional thinking? I mean, maybe just my own sense of it is that it enables reasonably accurate results of fairly standard buildings in a way that promotes code compliance and so on, but it may leave you short on things that you may say nature provides something, but as Caitlin said, you can't simulate it, so you don't do it. So maybe we acknowledge that, but what do you see? I mean, do you see a way forward that would get at more of the intuition, the exploration of things we see around us, and wonder, can I utilize some of that in the in the built environment?
It's a great question.
A new Energy Plus, the Dogan version.
Oh no, I don't want to develop that myself, but I think you're getting at a really good point. I mean, Energy Plus as an engine is built by many people over many years, so I think it would be very silly to throw that overboard. But there are moments where there is this frustration that you mentioned, that it's constraining you because it has modules that were designed to model a certain thing, but you can't really be creative all the way. Right? So I think some of the work that one of your students showed today, Edu, I think that was quite impressive. To see is not that easily kind of modeled in a software like Energy Plus. But I think what needs to happen is that this software gets a proper programming interface so that you can do customizations of it. Because I think there are certain models in the tool that are powerful and strong, and they're correct. They've been validated over many, many years, and there's so much funding been poured into it. I don't think it's good to reinvent your own, but I'd rather see something that extends it and makes it more flexible in that sense. Yeah.
That was super great to see. I have a pretty depressing thought, and I wonder what you think about it. Because we always talk about, sustainable design, and of course all architects are in love with it because it's form-giving. But are we not too late? And don't you see that, like, society has moved on? There are billions of dollars that are now invested into the building stock. Nobody talks about a Trombe wall. They talk about you get money to weatherize your building, to put insulation outside, to put a PV on your roof, buy a Tesla, and have a heat pump. And so nobody wants a passive system. And I feel like the rush in architecture towards the embodied energy is because that's one of the last domains that make an important difference, but the architects can also make a difference. So maybe this whole notion of vernacular will disappear, I don't know. And plus it's really hard to model because we've been trying to model some of these techniques, and it's hard. Is it ever gonna, are we too late when it's finally not hard anymore to model this?
I mean, I think these are all, they're maybe smaller niche solution, right? Anyway, and there always have been in a sense. But I don't think it's too late. I think there are other kind of really interesting things you could play with. I mean, I'm always thinking back of this book, The Thermal Delight, in architecture that also came from BT, a BT student, I guess, at some point. And I think that's where it becomes really interesting for architects, again, to talk about comfort and well-being and sensation of space and providing kind of these kind of diverse experiences. And I think that's where you can then kind of implement some of those ideas, the vernacular ideas, if you will.
Are there any questions online in the chat? I tried to, I don't think so.
We can't end on that depressing note. So we keep saying even an architecture student or even a student can implement it. I don't think that's the bar. I think the bar is even when a middle-aged faculty member or practitioner can implement it, that's the bar for when it's easy to use. I think they're gonna blow us away. So anyway, I just wanted to say thanks again.
Thank you.
I have one last question. Moving towards big data, what do you think is kind of the most exciting part for you about the prospect of having kind of IoT sensing, and you worked with the smart city in Toronto. What is the most exciting and maybe concerning part of that future to you?
Smart cities are scary, for sure. No, I think for me the information that gets at kind of like the decision making of humans in their daily life is very interesting. Like how do we move about? Where do we like to spend time? I think that's kind of in the intrinsic interest of an architect, because that is a way for you to understand whether you were successful or not designing the space. And I think that's you know, for an architect, a very, very interesting data set, and that I would love to see being collected. It's maybe the response to spaces that I think would be very interesting to collect information similar to this kind of view exercise that we did. Because if you think about that, the way we do the survey, it's incredibly simplistic, just so that you can kind of get started at least, right? But there are so many more thoughts that go into designing interesting spaces with view relationships between spaces, between the activities that you're doing in spaces and the people that are in the spaces. So capturing these kind of things would be very interesting to understand, and how does that impact your overall happiness or well-being? Yeah.
Thank you very much.
Yeah, thank you so much.
Thank you.
Thanks a lot, Timur. Just to close the evening, I have some words from the department still to share with everybody. Thank you all for joining us tonight. We want to specifically thank the staff, the students, and I guess the faculty I'm reading here who made this event possible. And we hope that you will join